Okay, great. And we can see you, Zach, as well. And then I'm gonna. Okay, great. So this has been a really fun, set of specific, people bringing their own perspective to this problem. I wanted to start this afternoon discussion about this term fear, or to be afraid, right? So that's the name of this session, is bumping into things, robots that are afraid of contact. I feel like we've seen, a bunch of different interpretations of what that fear is. Maybe it's fear of dropping objects if it's an unstable grasp. Maybe it's a fear of falling over. What is it that we're fearing? That's what I really want to come away with. How do we define risk? How do we define failure? We've talked about failure a lot throughout today, but people mean different things. And so this could be a question of frameworks, of metrics. What do we have available to define these things? What's feasible to measure? Is there some cohesive perspective that we want to take? And so let's just dive right in. So given the diversity of contact conditions and scenarios, how do you define risk? And do you start to see some themes emerging from today's workshop? Maybe I'll start there and see if that's enough to get you guys started.
For me, can you hear me? Yes. So there are many aspects. First, the hardware should be suitable in order to perform these tasks. I mean, especially if you want to use collision, bumping into objects, there is the risk that the hardware can break. Right? So that is definitely something to consider. And not every hardware is suitable for the kind of motion that we are considering. So that's the first fear that I think one would have. And I think it was nice the last talk when talking about design. And so the hardware should be designed for that part of task. And standard or classical industrial robots, they were not meant at all, and they are still not meant for having collision or contact at high speed. So you should not really try to use them for that reason.
Yeah, for me, I think, I'm not really afraid of contacts per se from an optimization perspective, especially given the way we are doing it is by sampling from the simulation. What we fear is if there are too many contacts, then the exploration problem can become challenging. And then the other thing is, if we put robots around humans, we cannot guarantee safety given the kind of methods I discussed about. So, those are maybe the things that, we think about in terms of contacts and getting worried about them.
So I think I will just talk about my perspective from the Lego locomotion part. I think Lego robots shouldn't be afraid of making contact, because breaking contact is just a natural part. It's a natural inherent property of Lego locomotion. So if the contact, instead of being afraid of contact, we can actually exploit contact to improve the performance walking and ensuring stability. For instance, when someone pushes the robot really hard, the robot can take steps that's making contact, breaking contact with the ground. That helps with ensuring stability. But there are other types of contact that can cause failures. For example, losing stability. For instance, the video I showed earlier today, when the robot bumped into the rails of the treadmill, that actually caused the robot to fall off the treadmill. So that's the type of contact I think we should try to avoid.
Thanks for the question. I think we saw today many examples that contacts in some situations are unavoidable. In others, I think mostly in industrial context, in which often robots are used planning not to have contacts, while enabling having contacts will enable to enter also automation in fields where still is used now is required to have human labor. So I think this is very important field also to enable to reduce manual labor, especially where it's very I mean, time consuming or very repetitive, also reducing the effort for workers. So this is a very important point. At the same time, we need, as was previously mentioned, to enable hardware, to have a proper hardware that can afford the contacts. We need algorithms that take in consideration collision and contacts. At the same time, okay, I'm not going to comment more on metrics because I think I talked already about this, but we need also to define what is a reasonable level of contact that we may require the robot to cope with, because also us as humans have some limitations. I mean, we cannot think that a machine can handle whatever kind of impact or contact conditions. So I really think we need to understand what is a good level of robustness or resilience, if you want, for a specific application.
Zach, did you want to chime in on this?
Yeah, so I think I just want to chime in on some of the things that were said, specifically about legged robots before. I think like right now, if you look at, kind of state of the art controllers for these legged systems, which is where I have more experience and not really doing any manipulation, they're really only reason about contact with the feet, with point feet in the controllers. So if you talk about push recovery, they're able to take steps to not fall over, but they're not able to reason explicitly about contacts with the body or, even like other parts of the leg, like in general. So I think the ability to actually in our control algorithms, especially online, to reason about unplanned contacts with parts of the body that we don't explicitly sort of a priori, mark as being allowed to have contact is still like very scary and a thing that can easily cause our systems to fail. And I think being able to reason about more general contacts with our robots in the wild is super important.
Thank you. And before moving on from this topic, I want to sort of push this group again. So one thing that I think of is like a small child is running and it's falling. Instead of smacking its face on the ground, they might put their arm up and break their wrist. Okay, that's a failure, but it's maybe not as bad as a concussive event. Right, so maybe there is this spectrum of failure, and maybe we even want to call good performance failures. So what do we call a failure now that isn't actually as bad, and what do we call performance that is actually a failure? And what I mean by that is a glacially slow robot where you have to speed up the video by 16 times. Maybe that's a failure of the field, right? Maybe it would be better to sometimes break. And so I really want to sort of pull apart this concept a little bit more and move away from a binary kind of like, that's good, that's bad.
I loved that and would love to jump in if no one else wants to.
Go ahead.
So I think what you're getting at, I really like two aspects of this. One is like this idea of control to minimize damage. I think is super interesting, like in the falling scenario. I think that's something we don't even think about, right? And I think the whole topic you just, I think like that you just talked about, I think really is getting at the heart of like robustness and from a control perspective. And it is something that like we've thought quite a bit about in my lab, and I think it's super, super hard for all the same reasons. Like doing any sort of classic robust control stuff is hobbled by all the non-smoothness issues. And I think we are like really bad about reasoning about robustness in these contact settings. I think it's an awesome way of posing it.
Yeah, I mean, I really like the point of, the robots being really slow and the need of speeding up the videos many times. So I feel like a lot of the times when we are solving optimization problems, we are not leveraging the solutions that we have found in the past, in the sense that we are, we are not warm starting them. So I think, there's some exciting work happening both in the model-based and the model-free camp, right? Where model-based people are trying to warm start solutions or get, good initial guesses. And I think if you look at reinforcement learning based solutions, they're actually doing amortized inference at deployment time. So I believe with these kind of techniques, we'll get closer and closer to real-time feedback control.
I just have 2 points to add. I think it's an excellent question about how to reason about risks and failure with the scope much larger than just locomotion tasks. I think in order to do that, so first, I think maybe we need to enlarge the operating condition we consider when we design algorithms. So instead of just focusing on locomotion and the lower limb of the robot, we should look at the entire body and also different types of tasks when we design algorithms. So enlarge the operating condition. And also the second point is instead of just value the stability as a top priority and maybe robustness with certain conservative bounds to evaluate performance, maybe we should also enlarge the values we care about when we design algorithms and maybe prioritize these values based on specific tasks and robot platforms and scenarios.
For me, as well, is not there's not really a dichotomy, and you should say, I mean, successful, not successful. And I completely agree on the fact that sometimes you should really look at failures and learn from it, in the sense of, maybe an expected motion is happening, and out of it, some emerging behavior is discovered, right? So making mistakes and might actually allow to find a new policy, new way of somehow finding a new local minima that you were not able to find before. So I think that's also why how we learn by simply making mistake, we end up in a completely new space, new area where actually maybe we perform an action that we thought optimal in a better way. So so definitely that there should not be fear of failing in that sense, and you have to. There are two things that when the motion is not happening as you intended, that you can try to do: either evaluate if actually it's a failure, or maybe you actually discover something new, or try to then learn how you can actually cope with that deviation if it's really harmful. So there somehow once a failure has occurred, you have really to evaluate if that's really a failure or maybe a feature that you were not able to discover otherwise before.
Also, to add another point to this, as a human, if we take us as a reference, when an injury happens in one of our limbs, like if you have an injury in one leg, actually, we find ways to cope with it and to locomote in any case. So this, I think, it can be another good source of inspiration to have more adaptive algorithms that take benefit of the remaining degrees of freedom that a system has, even after a failure, that maybe you may lose the degrees of freedom or the capability of controlling something if you have damage in one of your sensors. So this can be also a direction to look for. At the same time, also to increase the robustness, or the physical robustness of the system. Something that we can think of is to protect, for instance, more sensitive elements, to add mechanical fuse to the structure in order to protect more delicate components.
You mean like a mechanical fusing, that kind of thing? Mechanical fusing?
Yep.
Yeah, very cool. Yeah, from the audience.
Yeah, I guess I count as audience. I guess another question that I was thinking of when we were designing this workshop was, if you picture yourself going down a hallway and you're not really paying attention, you might sort of bump into the side of the wall and you keep going and it's fine. And I think most robots that would be defined as failure. Most of the stuff we've seen today has been really focused on, doing intentional contact better. What do you guys think about sort of unintended contact? Should we be planning for acceptable unintentional, sort of indifferent contact? Like, all right, I know I can bump into that wall, so I'm not going to try and avoid it or make contact either way. Or what do you guys sort of think about this less sort of task driven? I got to make this contact to walk, right? And more, rubbing your body on the wall or bumping, you know, I bump the cup a little bit as I'm going to reach for my cell phone here.
Oh, indeed, one of the point that was made but it was not covered in my presentation was this aim-aware collision monitoring, and that's exactly what you are describing, the sense that indeed there is an intention, but somehow after something has occurred that is not, you know, as you intended, you have to evaluate if that is catastrophic, or if you can actually ignore it and continue as if it hasn't occurred. Indeed, certain situation you want to have a certain type of motion, but you know, part of your body hits a wall that was not perceived. And as long as the state after this jump is not that far from what you wanted, you can probably just ignore it. So it's important to figure out, indeed, to be able to assess if whenever you have a collision, if this is somehow really stopping you for continuing the execution of what you wanted to do, or if it's something that you can recover from activating a reflex, or really if you have to stop because there's definitely a completely wrong assumption about the environment or yourself that you have to correct. So I think that the ability to quickly discriminate and understanding what happens is essential to make it robust and then flexible depending on what is happening.
Maybe to add on to that, right? So I think once we think about making contact, we think of all objects being the same. In the sense, we're not distinguishing between something being more pliable versus something being rigid. I think this is where maybe recent advances in perception can be very interesting, right? Because if there's a leaf, it's still a barrier. If I use a point cloud camera, it was just going to say it's a barrier, but I know that I can go beyond the leaf, right? So kind of having idea of such affordances, which are, you know, either learned in a self-supervised way, which I think some works have been exploring, or either we bake in this knowledge, but I think we need to go beyond height maps or just depth maps. And that might really enable us to make these, we might not care, right? Okay, if I touch, it's okay. If I don't touch, it's, you know, it's still okay.
Yeah, I think it's right now for like locomotion, it's kind of tricky to handle uncertain contact modes with uncertain timing and uncertain contact sequence or contact order. I think maybe one potential way to address this is fast replanning that reasons about all the maybe the key possible scenarios, the contact mode after the unintentional contact occurs. That may be one potential way to address that. So with that, we need maybe a better model and also a planner that can reason about these type of new uncertainties. And I just listened to the poster by Michael Posa's group and Alp's work. I think that's maybe one potential way to solve these type of problems.
We have another audience question.
Hi, thank you for the panel. I'm thinking that the question about fear and also about unintentional contact makes me think that some of the fear that we have of robots maybe doing this unintentional contact is about damage to the robot, damage to the environment, or like loss of all of the hours that we've put in. So tying this back to the discussion of tactile sensors from this morning, where we were talking about how biotech is very expensive, there's not really these things available. How do you think maybe sort of either making the environment safe, the robots lower cost, sensors, like how would these maybe help reduce fear and increase in unintentional contact?
So I think it's an excellent question. I mean, if we have to look at biology, right, as when babies begin, they don't apply that much forces, right? Their bodies are just, sorry, incapable of doing it. So maybe when, you know, we are exploring, you know, we could explore in a way that we don't apply too many forces. You know, that could be one way. I think we do need to experience contacts. So we can't just play safe all the time. And the other thing that you're alluding to is, you know, if we have cheap hardware, then we won't really worry about, you know, the hardware breaking down, and we can do many more experiments. So, I mean, I definitely think, you know, the field is going in that direction, but still we don't want to, you know, break hardware. So maybe doing that in simulation and somehow learning it over there and then transferring it. So I think, so maybe if we have really good contact rich simulators, which can simulate many contacts simultaneously, I think some advances over there would be really, really helpful.
Great question, thank you.
You know, I fully agree on this idea that exploring somehow the limitation progressively, you know, moving slowly at the beginning and then accelerating. At the same time, what I think that, I think this is happening already in the field. I mean, there's this idea of soft robotics now, where you're starting to get closer to human or anatomy or animal anatomy, where you have a really hard core and a soft somehow shell. And this thing is actually allowing precision as well as, I think, compliance. But one thing that nobody's talking about, I think, it's also damping. I think damping is extremely an important factor, especially when you start going fast. And I think, for example, series elastic actuation might have a problem there also for this reason. You just have a spring, you don't have a damper. So I see also a lot of research now on adding viscoelastic elements. And so somehow something in between compliance and rigidity that might be interesting, or I see quite promising.
Thank you. Okay, we have a hand raised online. Go ahead and just unmute yourself.
Yes, so building on top of the previous question about maybe some cheaper sensors encouraging more experiments, and also the soft robotics part. You know, there has been some work previously about inferring contact and even contact forces from just RGB images. Like, you know, you can look at the distribution of red color in your fingernail as the thumb is pressing down to figure out how much force it's applying. Or if a soft finger is pressing down and it deforms slightly, those small deformations can tell you how much force it's applying. So those kinds of inferences might be possible just using a cheap RGB camera. Do you think those are useful, or they have some limitations?
And I might actually dovetail that into one of my own questions, which is around sensors and, you know, real sensors. You know, we have this sort of simulation. We're doing a lot of trying to understand the physics of what's going on. Versus a real system having real sensors with real error. And so this question of implementation around that, maybe what is it that you value in your field of work around sensor integration? Sorry, was that
You know, there's one of the things that I think is also quite important is that sometimes you don't really have, you don't need really fidelity, for example, in simulations and sensor information. So how you actually encode your motion, how your controller is developed, or your sensing is developed, might not really have to represent 100% of reality. So there's a lot of, you know, somehow trying to figure out exactly how you want to encode, how do you want to simplify it, or how do you want to design your control and sensing strategy in order to compare simplified description of the dynamics of the robot or that you have, and how to compare this with actually what you sense. So that you might have a lot of information, a vibration, oscillations, all things that you cannot really encode in the intention and the model. That's not essential that you actually try to put into your system model, but you should be able to then compare reality and sensor information with the simplified assumption. For me, for example, post-impact oscillation is one example. Sometimes you don't really need to have those kind of phenomenon modeled in order still to perform fast motions with impacts.
Yeah, I think sensors are really important because with better sensors, it opens up opportunities for improving the performance of algorithm design, for example, planar and controller design. So with Lego locomotion, for example, if we have cheap force sensors that are fast and accurate, then maybe we can mount them on the robot's leg, the leg or the feet to help with contact detection. But right now, the force sensors on Lego robots are, if they're expensive, then their performance are most likely to be better. But the reality is they're just too expensive to be equipped with commercial robots. So for instance, with a DJ robot, it doesn't even have a force sensor. It just use forward dynamics to estimate the forces. But if we have that reliable modality of sensing, then it can help with state estimation, planning, and control.
We haven't heard from Zach in a little while, so.
Thanks for, yeah, I guess on that, I'll offer an anecdote. We have some Unitree A1 robots in our lab that are, they're fairly cheap. They're like, I don't know, 10 or 12K quadrupeds, and they have pressure sensors in the feet that you're, theoretically supposed to use for contact sensing. And we've recently been messing around with these in the context of Kalman filter, like state estimation stuff, just trying to do contact detection. And it turns out the pressure measurements are so noisy that the contact estimation is so bad that we ended up doing better just looking at like mismatch between our sort of forward kinematics velocity and our expected velocity and this kind of thing in the filter. So we're actually not even using the pressure sensors in the feet that came with the robot right now, and we're doing better than using those sensors. So I think this question of contact sensing is huge. And yeah, there's some good options, but they're super expensive. And there's really nothing out there at this low cost end that is worth it as far as I've seen. And yeah, I think there's definitely some work to do there. I think there's also though probably some things we can do with a bit of algorithmic cleverness and sensors that we do have that are cheaper. So like a maybe a dumb example of this is we've started to think about, well, can we throw IMUs all over the robot in various places? Like, can we throw IMUs in the limbs and use those to infer contact information and things like this? Because gyros and accelerometers are pretty good and pretty cheap, and we can buy these for a few bucks. And so maybe that's a way of getting at some of this stuff rather than explicit like force or pressure sensing in the feet. So I don't know. I think there's definitely, I'm not a sensor developer, and so maybe we're going to rely somewhat on people who actually do that low level work. But I think there's definitely room to play with currently available cheap sensors in creative ways to eke out some of this stuff. And yeah, I don't know. Love to hear other people's thoughts.
Great, thank you so much. And I think just to end with one fun, fun for us question, which would be if you had sort of like a pipe dream demo, maybe it's well within your field, what might you think of? So like I would think of something that's like a kid, so that you're running along, you kind of just face plant, and then you kind of jump up and you keep running, something that where the hardware can kind of get injured and move forward. So, sorry to put you guys on the spot, but if you have just like, oh, that would be so cool, it'd be great to end the day on that note. So maybe like 2-sentence.
So should I start? Yeah, what I was suggesting before, like a hardware that is capable of recognizing what's still functional, what is not, and self-adapting to that, and finding ways to be still functional. That's would be a good focus for me.
Almost like a sense of pain, I guess.
Yeah, I think the type of manipulation that also we saw in the last type of video and presentation, as well as many of the ones I was presenting, with this idea of being able to, I don't know, removing very quickly boxes from a pallet, or really something fast. So that will be something I think that will impress with the ability to really also manipulate in hand, and also exploiting gravity. I mean, these things are really probably the vision.
Cool, thank you.
Maybe something more wilder like robo rugby, where there's rugby between robots and humans. You really have to push and make use of contact.
So collisions, purposeful collisions between people and robots.
Purposeful, adversarial.
Okay, adversarial.
I guess one fun demo I've been thinking about is to have a Lego robot walk or run in a concealed space that also rotates or translates, and also the space doesn't have just with random motion, and the space is concealed, so the robot cannot see the landmarks on the lens to help localize and itself. So yeah, I think that would be a interesting demo.
That'd be cool. And Zach, do you want to finish it up?
Yeah, I would, as a more of a locomotion person, I would go for like some kind of extreme obstacle course along the lines of like American Gladiator that I remember watching as a kid, or like Most Extreme Elimination Challenge. What are these things where you have like monkey bar things and having to swing over things, like where you actually, it's like sort of a, I see it as almost like an in-between between manipulation and locomotion. Like you actually have to use the environment in very creative ways, like rock climbing and these sorts of things to get yourself, you know, through some complicated environment to a goal, and use contact all over the body, right? This kind of thing. That would be my
Well, that's a lot of really rich contact that we just came up with. So let's go out and do the science. Aaron, did you have any last announcements before we call it a day? No?
Thanks everyone for coming and sticking around for a long day. It's also at the end of a long week for many of us. And a holiday weekend.
And I would like to thank Aaron for leading the charge and organizing this. Thank you so much for all the work you put in. Okay. Have a good one.